So say we're given a linear system of three equations and three variables like so. We've got 3x minus 2y plus 3z is equal to negative 4 as the first equation. 2x plus y minus 3z is equal to 2 as the second equation. Let's clean up that y a little bit. And then the last equation is 3x plus 4y plus 5z is equal to 8. So let's label our equations 1, 2, and 3 so we can keep track of what we're doing. And the first thing we want to do is to pick what variable to get rid of. Now, usually what you have to do is pick two different pairs of equations and get rid of the same variable in each. So the trick comes in finding what variable is the easiest to get rid of. Now notice between equations 1 and 2 that if you multiply equation 2 by 2, then the y's are going to become opposites. They're going to have opposite coefficients, which means that when we add them, they're going to cancel out. And I also want you to notice that if we take equations 1 and 3, I'm just going to circle these two kind of like that, and you multiply equation 1 by 2, then these the y's are going to be opposites again. So it seems like our best bet is to take equation 1 and 2, and with equation 2 you want to multiply by 2. And then the second set, you want to take equation 1 and 3. And for equation 1, you want to multiply by 2. So this is the way we can get rid of the y's. And let's see if we end up doing this right. So equation 1 for the first set, we're just going to write as normal. 3x minus 2y plus 3z is equal to negative 4. And for the second equation, we want to multiply everything by 2. So let's get rid of all this color first so we can see what we're doing. So multiplying every single term by 2, we got 4x plus 2y minus 6z is equal to 4. So now adding everything together, we get 7x. The y's cancel out, which is exactly what we wanted. Then minus 3z is equal to 0. Remember, negative 4 plus 4 is just going to give us 0. It doesn't mean that the equation is unsolvable. 0 is just a value in this case. So now for the second pair, we want to multiply equation 1 by 2. So we want to multiply every single term by 2. So we're going to get 6x minus 4y plus 6z is equal to negative 8 as the first equation. And equation 3 we write as normal. So 3x plus 4y plus 5z is equal to 8. So now, for the x's we get 9x. The y's cancel out. Again, exactly what we wanted to achieve. And then we get plus 11z is equal to 0. This is an interesting set of equations. But now I want you to notice that with our efforts here, we've managed to reduce these two equations, let's call them 4 and 5, into a linear system with two equations and two variables. And we know how to solve this, right? So let's rewrite these equations. 7x minus 3z is equal to 0, and then 9x plus 11z is equal to 0. So now what we want to do is to cancel out one of the variables. And usually you end up picking the one with the smallest coefficients, although these seem to give us probably the same amount of work. But notice that the z's, one's negative and one's positive already. So I'm going to pick the z's. It looks like those might be easier. So if you multiply this top equation by 11 and the bottom equation by 3, then the top coefficient for the z is going to become negative 33z. Oops. And then the bottom coefficient for the z is going to become plus 33z, which means that the z's are going to cancel out when we add the equations together. So let's do that. So we're going to get 77x minus 33z is equal to 0. Remember, 0 times anything is 0. And then in the second equation, we're going to get 9 times 3, that's 27x, plus 33z is equal to 0. Now adding these together, we're going to get 104x, the z's are going to cancel out, is equal to 0. And the only way that can be true is if x itself is equal to 0. So now we have the solution for our x. But we still need to solve for y and z. So the first thing we should do is solve for z. So we can do this by plugging x is equal to 0 into equations either 4 or 5. So that way we can solve for z. Looks like equation 4 might be easier because the coefficients are smaller, so I'm going to plug it into equation 4. And equation 4 says that 7x minus 3z is equal to 0. Since x is equal to 0, that's 7 times 0 minus 3z is equal to 0, which means 0 minus 3z is equal to 0. So 3z minus 3z, is equal to 0. And the only way that can be true is if z is also equal to 0. So now we have x is equal to 0 and z is equal to 0, and now we have to solve for y. And the way we do that is to plug in z equals 0 into any of the original 3 equations. So into equations 1, 2, or 3. So let's take a look at the original equations. And what we generally want to pick is the equation that's going to cause us the least amount of trouble. And generally the equation with the smallest coefficients. So it seems like equation 2 might be the best for us. So let's rewrite equation 2. So we want to plug it into equation 2, which states that 2x plus y, sorry about that, 2x plus y minus 3z is equal to 2. Right? So now, we also want to plug in x is equal to 0. Sorry about that. So since x is equal to 0, we got 2 times 0 plus y minus 3 times 0, and that's equal to 2. And we know that anything times 0 is 0, so 0 plus y minus 0 is equal to 2. There you go. And so, simplifying this further, we have that y is equal to 2. So now we have our x and our y and our z, and we want to write our solution in terms of the ordered pair x comma y comma z. So we want to say the solution to the system is x, which is 0, comma y, which is 2, comma z, which is 0. And that is the solution.